Okay. So thank you for the organizing committee to bring this meeting in Rome. I think that, obviously the physics that the CPC or other plus-minus collider will allow us to probe is quite remarkable. We will be able not only to measure very precisely the Z, the W, and the Higgs. For example, you can see what the CPC brings in terms of precision coupling, understanding the precision coupling of the Higgs, but also, for example, you can see how remarkably you can search for dark matter with Z, for example, rare decays. You can see here that if you have another scalar particle that mixes with the Higgs boson with a coupling alpha, you can see, and as a function of the mass of this scalar particle, you can see what has the improvement with respect to what you have now at LHC once you will have this kind of machine. So this is absolutely beautiful. And to do this beautiful physics, you need a beautiful detector. So for the CPC, we have a couple of detectors. We have a baseline, and we have a couple of options, one with a low magnetic field of about 2 Tesla and a beautiful drift chamber, and another one which is a full silicon option that is also very interesting. But you can see from this picture, the tracking detector are sort of everywhere here, from the region around the interaction, where you have fantastic vertex detectors, to, for example, the TPCs that provide fantastic information on the particles, and then also in the muon chambers. So tracking detectors are everywhere. And of course, also it's very important the solenoid, the magnet that you put here. And we had a very interesting presentation about the possibility of using ITC superconductor also for that from Ning Fei Peng. Here is a tape of one of the superconductor, high temperature superconductors that was shown here, and it was already presented also, the R&D for this was presented already in the talk this morning for the magnets. Starting then from the vertex detector, we know already from a lot of the studies that for the identification of heavy quarks, B and C, this require really a very, very challenging detector. So here is a formula that tells you what you do in terms of R5 precision. And you can see here that you have to have a term A that is at the level of 5 micron. It's been put in the simulation that is done for the conceptual design report. And a term that depends on the multiple scatterings that is 10 micron. This implies that you need a space point resolution nearby the vertex of about 3 micron and a very low material budget of less than 0.15% per layer, low detector occupancy, but also this detector, it's true that the radiation damage is not the radiation damage of the LHC, but still, you have to have some radiation hardness also for these detectors. One of the R&D that is ongoing now in China is quite impressive, and there is a lot of collaboration with Europe, for example, in this case. And you can see here the work on the CMOS detector. These are Tower Jazz technology, 180 nanometer technology. The technology that is used now in the ITS upgrade, and also Atlas is considering a modified project also for the pixel, for the outermost layer of the pixel upgrade, the one that is the largest area. You can see here what happened with this technology. So you have a very tiny diode here that gives you a very tiny capacitance of the order of few femtofarad. And you can see here that when you have an epitaxial layer, so in this case, and you can see that here you have your electronics, that is a standard electronics that you have in your chip with CMOS amplifier, etc. And so you can see here that, that in this technology, by putting this deep P well, you can collect almost all the charge. So you will collect the charge that is generated here, the electron all pairs. You can collect them on the diode, and these other N-well, which will also act as a collection region, is shielded now by this process that has a deep P-well. So this has really opened up a lot of important application for particle physics. Furthermore, here you can also apply bias to these electronics, again, facilitating the collection of charge also by some drift. In China, there has been a first submission, which is called JADE-PIX1, which is a joint multi-wafer submission with France, with IPHC in France. And the original submission, the first submission, was done to understand a little bit the diode, really. And so by changing the dimension of the diode and optimizing it to obtain the best performance of the sensor. And you can see that there were two matrices, one with 33 micrometer pitch and one with 16 micrometer pitch. And again, they develop an excellent system of testing also these detectors. You can see here the detector mounted with, on a daughter board, then connected to the motherboard, then with an FPGA that is read out by this system. They've done some studies, obviously, with iron 55, with strontium 90. You can see here that you can see the peaks that you expect in iron 55, for example. You can distinguish the two peaks. And also now they've done irradiation in a reactor in China, Xi'an, and up to 10 to the 13, the doses that they need. And they are preparing for a beam test in DAISY, so stay tuned with the result on this performance of this detector. Okay, they are already so with a new updated detector, which is called JADE-PIX2, which is increasing the complexities that you have in this chip. You can see the layout of JADE-PIX2, and here is a layout of the pixel, which has a dimension now of 22 micron, where you have more components, not only changing the dimension of the diode, and they are testing a couple of amplifiers. They chose a diode now with 4 micrometer, and you can see here in terms of noise, in terms of loading capacitance, you can see that you reach a noise of about, the capacitor has a level of 4 femtofarad. So really, this technology allows you tiny capacitance, so tiny noise, and very good performance. Another detector that is under consideration for the vertex detector is a technology that is called silicon-on insulator, which is a technology that for a certain period had some problem, but now this problem has been solved, and there are a couple of sensors that are already taking data, for example, at synchrotron facility. And you can see here a picture of the silicon insulator technology, where you have a silicon sensor, high resistivity. Then you have what is called the box, where you have this oxide layer. And then on the top, you have the normal, in principle, CMOS electronics. And so by not having this interesting technology with the deep P well, you actually can save space, and you can put more logic into, more intelligence in your chip. So they're using this Lapis 200 nanometer process, which has full in pixel CMOS, 5 metal layers, and it can be seen down to 75 micrometer. And again, having this as layer can actually be quite thick. In the case, I didn't tell you, but in the case of the Tower Jazz technology, the epitaxial layer is really of the order of 25 microns, so it's very thin. Here, instead, this layer can be bigger. And so this gives you more charge, of course, and as I told you, also so a more compact electronics. So here you can see a couple of chips that they have developed, CPV1, which has a pixel pitch of 16 micron, and CPV2, which is an improvement of CPV1, in which you can also now, there was some problem, and you now can put some bias on the detector. So here are just a few results of the SOI. You can see the iron 55, they have here an iron 55 source that is impinging on CPV2, and you can see here as a function of the bias, you can see that around 40 microns, they are fully depleting the detector, and they get a lot of charge out of the order of 6,000 electrons. Also, with a very precise laser system that obtain a precision of less than 0.1 micron, they can measure the resolution that you can achieve with this technology. And you can see as a plot of the resolution in micron versus the charge of the electron charge that you collect. And you can see that at around 3,000 electron, you get a resolution of about 2.3 micron. So really very spectacular. Again, I told you already at the beginning that in one of the concepts, we are looking to a drift chamber. And this drift chamber is really, this is not your old drift chambers, okay? It's really a new concept that is called the IDEA drift chamber. And it's a novel method of building a drift chamber in which you really minimize mass at every level. You can see here that, in fact, it's transparent. It's so massless that it's transparent, okay? And you do that, so this idea was already sort of developed with the Chloe drift chamber and will be also applied to the MEG2 drift chamber, where you really need very low sensitivity to very low momentum tracks. And you can see here that, what you do is that you do it by reducing the material on your end plate, by reducing the thickness of your wire, and really by looking at putting less mass as possible in these things. So again, with the new technology, we can do much better than we used to do. And again, here are some numbers, okay? You can see that you have a reduction of the material budget to about a per mil of radiation length for the inner cylinder, and a few percent of radiation length for the end plates, including the high voltage, etc. Because your wire are so thin, you can go through a fish-through wiring, which allows to increase the chamber granularity and reduce the multiple scattering, of course. And again, also to cluster timing, which allows you to reduce the resolution down to 100 micron for a cell of 8 millimeter. And again, also using very low mass also gas. So for example, helium-based gas mixture. You can also use cluster counting for your PID, for your particle identification. And you can see again here what you do with the standard technique in the dashed lines for distinguish Paon and Keon, etc. And then instead with the full line, what you do with this technique. Again, a fantastic performance, a beautiful chamber. Again, in terms of idea for CEPC, we are looking at about, they're looking at about, you have a baseline and then a couple of options that they're looking. You can see that there is still some work to do in the optimization of this option. Here is a picture, for example, of the momentum resolution and the error on the momentum resolution. You see here that at low momentum, with one of these options that has a larger drift chamber, you don't do quite as well as the baseline option. But again, with the optimization of the layout, I'm sure that you can do better. This is also the fourth concept at ILC, and here is a plot, for example, of the result of a simulation of the H going into mu plus mu minus x from that application. So then there is a full full silicon option. There are two designs of the full silicon option. One that is called CPC SID, because it's inspired to the SID solution, where you replace the TPC with extra silicon strip barrel ladders and end-cap disk. And another one that is called SIDB, where you expand the SID design to a full tracking volume. And again, there is a link to a lot of work that is done for this option here. So the B field is assumed to be 3 Tesla. And the radius of the tracking volume is set to 1.87 to don't change the size of the calorimeter. And again, there are 3 options also for the configuration of the barrel layers and for the configuration of the end cap. So there are, of course, there is still a lot of optimization. So you can see here a few outcome of the simulations that has been done in terms of performance. There are many reconstruction tools that are now available for tracking a fit, both with more standard silicon tracking and also using conformal tracking. And again, you can see here a plot of the Higgs mass, where you can see that in some of the configuration of the tracking, you have a little bit of some problem. And also here for the Z going to tau tau, where the tau goes into 3 prongs, you can see that you have a little bit of loss of efficiency with respect to the more standard simulation when the 2 pions are close. And again, there was a very nice exchange, for example, with the people that with Emilia Leogrande, who is doing similar work for the click framework about how you have to deal with the conformal tracking in order to solve some of these problems. So there was a lot of interesting discussion. So here is a plot of the CPC-TPC, so always going a little bit outward. You can see the dimension of 3.6 meter and the length of 4.7 meter, 3 Tesla magnetic field. You try to achieve 100 micron position resolution in R5. You have big numbers of 3D points, about 220. You achieve DDX resolution less than 5%, tracking efficiency of 95% above 1 GeV, and a tweet resolution of 2 millimeter and the momentum resolution of 10 to the minus 4 per GeV. So very impressive performance. Again, a standard problem for TPCs that has been known since the time of LEP, I think, is what the distortion of the drift field where you collect your charge due to secondary ions produced in the amplification region, which it's denoted as ion backflow. And again, they are trying to, there is a lot of work done now in China to try to correct for this problem. For example, using gating devices with open and to stop this flow. And here is again a plot that has generated a lot of discussion because you see in the IBF performance versus the gain. You can see that with higher gain, it looks like you have a smaller amount of IBF. And again, there was a very nice discussion with Werner from Riegler from Alice, saying that this, in fact, is not perhaps what happens, and that the way that you're doing this measurement is actually biasing you because you're using very intense X-ray, and by diminishing the intensity of the X-ray, you would get a better idea, more precise idea of the magnitude of this problem. And one has to be careful because Alice had to found out this problem on their own. and then also a laser calibration signal for the system, for the laser to trying to calibrate out this distortion. And you can see actually that this system is already under construction with a small prototype. So really a lot of development also in this respect. Of course, if you want to achieve the performance that I denoted before, you must have very low power electronics because you are going to have millions of channels, okay, 1 million channel. And again, there is a lot of work on a low power 65 nanometer chip that achieves that. And you can see here the design of this chip. There have been 3 prototype chips that have been designed in the first multi-wafer run with a different front end and various options of ADCs, okay? And you can see here a plot of, first of all, is like the power consumption that they measure on this chip is of the order of 2.18 milliwatt per channel. And meeting the specs that was put on this parameter, which was 2.5 milliwatt per channel. But also, you can see that in terms of noise requirement, again, you can see the electron equivalent noise in terms of the input capacitance. You can see that they're doing better than expected. The goal was 500 electrons, and in fact, you might, well, it depends a little bit on how you do this fit, but again, it seems that it could be lower than 500 electrons. In terms of Muir detectors, we had an overall presentation from Paolo and then a couple of presentations on different technologies. So you can see here the configuration of for CPC, where you have 8 layers of RPC station. And there are many other options that are under consideration, so drift tube, sync-up chamber, micromegas, and GEMS. What is interesting is actually that we had also a big discussion about that, comparing, for example, the number of stations that there are in the ILC detector and here, and even wondering if muons detection is still important once you have this fantastic calorimeter. I mean, can you do everything with the precise calorimeter, or do you need in the plus and minus also many drift chambers? So there was really an interesting discussion. So again, you know, this drift chamber has 10,000 square meters, so they're quite big. Okay, so one of the new technologies that is under consideration is called the micro R well, and you can see here of a picture of the micro R well, where you almost have sort of a half of the gem, you know, configuration. And so this configuration actually, it's more suitable to be industrialized, and it's been partially already industrialized. You can see here, you know, you start with this Kapton copper level on a resistive stage that then can be etched to form these gaps, these holes in the things. And then this can be done, the gaps have to be done still in Rui's workshop at CERN, so it's not completely industrialized. I don't know what we will do when Rui is retiring, you know. Luckily, I'm working on silicon, so I'm okay, but he's young, okay? Time is going by, so, you know. So anyhow, and then, you know, you have like a pad layer that you can sort of plug together. And so it's a much easier way of building a detector than with GEM and other micro pattern gas detectors. You can see here, this is actually one chamber, okay, that has a dimension of 1.2 meter times 0.5 meter. You can see here, you know, the chamber with the readout electronics here. And so in principle, it's low cost and can become even lower cost. The position resolution is of the order of 5 to 10 millimeters, and the time resolution is 1 nanosecond. And you can see already technology transfer with Eltos, with the Eltos company. So you can go and almost buy it, not quite. Okay, so this muon detector configuration is also used for the idea detector for SVCAE, where you have 3 to 4 MGDP station interleaving the iron yoke. And the current baseline uses this micro Arwell as well. So what I think that was especially useful at these sessions that we had for the tracker is really so to bring in other community. I already told you, the discussions that we had for the TPC, but also there are other communities that are using the same technology, for example, for the vertex detector. And they are using it for detectors and upgrades that are, starting very, very soon. So it's very interesting. So here is actually the same, a picture of the same tower jazz technology that I showed at the beginning. Again, in the case of Alice, there is a picture of 21 times 27 micrometers square. It's low power consumption, 40 microwatt per centimeter square. Input capacitance, 5 femtofarad. Input charge, about 1,300 electron. Spatial resolution, 5 micron. Radiation hard, almost at the levels that are needed already for any plus or minus machine. So again, once you build such, you construct such a beautiful detector, the mechanic has to match it, okay? And in fact, you can see you have 7 layers with ultra light support structure and cooling of the order of 0.3%, X0 for the innermost layer, for example. Here I have a picture of the outermost layer, but you see that the structure that supports the ladders is practically, is practically empty. It's very light. It's with this carbon fiber. And you can see here one of the ladder, and the detector is under construction and has to be installed in the next shutdown. And again, it's possible to remove it and reinstall the detector for maintenance in the early shutdown. So again, we have to keep an eye on this community because it's doing stuff that we want to learn from. Again, they're also thinking about, Alice is also thinking about the future. The top is really, the future is already here. This is a modification of the process, which is published in NIM, which is already under configuration, for example, with Atlas, where you have this layer, extra layers that allows you to be more radiation hard. But again, here is from RAL, a picture of what you can do with stitching. By stitching together this detector, you can have a larger detector, and this is a technology that exists at Tower Jazz, as you can see from the picture. Again, migration from 180 nanometer to more modern technology, and so you will be able to put more intelligence on the chip itself. And of course, the flexibility at the end, when you have ultra thin silicon, you can bend it, okay? Can you really do something better even in the technology? Again, Alice has a TPC, and that's why Werner, had a lot of input on the TPC for CPC. You can see the picture of the TPC that they have now. It has a diameter of 5 meters and a length of 5 meters. It uses this gas mixture, a drift time of 100 microseconds. You can see the sector on each side of the TPC that have 18. You have 18 sectors with, you see the inner chamber and outer chambers that are called IROC and OROC. And again, in the current detector that has taken data in run 1 and run 2, you have, this is made up of 72 multi-wire proportional chambers and about 550,000 readout pads. Again, this is rate limited, and so for run 3, before run 3, Alice had to do an upgrade. And you can see here what they've chosen for the upgrade. They've chosen a solution to, again, for this ion back problem, they've chosen a solution with a stack of 4 gem cells And you can see like the gem cell, the gem layer are all different from each other. And you can see how the stacking is done in order, and all optimized in order to reduce this problem, okay? And you can see here the production of this IROC and OROC is continuing until September 2018. So they should be finished at that point. One of the things that, again, the community can bring from outside is also the work that we have done, for example, also for Atlas, for the collider, in terms of lighter support structure. And this has been described by Tim Jones. And you know, a lot of what we do, it has to do with carbon fiber, okay? And again, there is a lot of new techniques that you can implement in order to make this laminate perform even better. And you can see here a picture of some of the curings that you can do by putting this structure with waves of carbon fiber that are going in different directions in order to keep the structure flatter and balanced. And again, you can really do what is called a spread-to-prepreg technique in order to spread the strips. And again, in general, this technique done in industry, the strip have to be about, come out to be about 15 millimeter wide. And again, you can change this and do it better and have a weave of 5 millimeter, which is more suited, for example, for vertex detector. Again, and this is what, for example, is being used already now in order to make the ITK much lighter than, for the Atlas upgrade, already much lighter than the first detector. Okay, so I showed you how you learn, for example, by putting together the experience from Alice, from you know, even from Atlas and LHCb, for example. Some of these microwell chamber are considered, for example, for LHCb, you know, into CPC. But of course, there is also the R&D that is ongoing for all of the other projects, like for CLIC and FCCE. And again, Emilia Leogrande did a very good job in summarizing some of you know, the performance of the CLIC and the CPC detectors, and also the R&D. And again, as you can see, there's a similarity again of the R&D project. Again, you know, CLIC, for example, has done you know, R&D for hybrid planar sensor, capacitive coupled HV CMOS, and monolithic high resistivity CMOS, and monolithic SI sensor. I don't like so much this HV-HR division. I really prefer to call them depleted CMOS, because in a lot of cases, like for some foundry, you really have an HR process that can be depleted, and also you can put voltage. So there is a little bit of weaving between HR and HV technologies that we should acknowledge. Here again, you see again the pictures that I had almost at the beginning with the tower jet technology. And you can see that in this case, they are using this modified process that is already a little bit more radiation hard. And again, they are doing tests with the investigator prototype chip. And again, I'm working in Atlas, and I'm doing tests with a similar investigator chip. So we are all using the same devices, okay, to optimize this technology. And again, there is now a chip that is under development, which is called CLIC-TP chip, which has a pitch of 30 times 300 micron, and which can be seen to 50 to 100 micron. And again, they're planning to use a smaller process in the future in order to put more intelligence and making this pixel chip smaller, in order to put not only the diode, but all of the intelligence, all of the digital electronics that is necessary to operate this chip. Okay, so I'm at the conclusion, and you know, you remember the say that all roads lead to Rome. It's true, huh? And again, I would say that also you have done a good job to bringing the R&D that is going on for tracking all year in Rome, you know, for and really, and this has really enable a lot of interesting discussions in our session. And so again, I really think that the organizing committee has done a good work. But I think that this also tells us that we have to continue to talk together, both from the experiments that are in the future at ILC, CLIC, FCCE, but also talking with the experiments that are running and the experiments that have very soon upgrades, because they also are doing a lot of interesting work. Thank you.
Any comments?
So I'm referring to the question to everybody that spoke about it.
No, you have shown that there is a lot of interest for options with the full silicon trackers. I wonder if there was some discussion about how to make the technology cheaper to cover these very large areas with detectors. Because
we didn't have this discussion. On the other hand, I really think that at all levels, this CMOS connection now, it's really opening new road. For example, for Atlas, there was some R&D that was done where you use the foundries that do CMOS chip to fabricate CMOS detectors. So you could really do strip detectors that are cheaper, you know, not strip detector, but maybe, you know, using also pixels that are configured together and read out at the end so that you have a mini strip, or, you know, you can do different things and they could be much more cheaper. And in general, if you go to the CMOS technology, because you have larger foundries, you could gain in cost. And again, even with the stitching, you could do better, you know. And again, so I do think that the CMOS really opens the way to cheaper all silicon solutions that we have maybe to re-optimize again, okay? I think that Marcel wants to say something about this.
I wanted to comment on this, and then I have another question too. Right, so yeah, we know that CMOS is cheaper per square centimeter than detector-grade silicon, so there's a bit to be gained there. And then the experience from costing ILC and CLIC detectors is that, contrary to what we've done before, the tracker cost is negligible nearly. There's so much silicon in the calorimeter. The calorimeter is so complex that dominates.
Well, already in CMS, for example, the high granularity calorimeter is like 600 square meters. The silicon is only 200. So, you know, really already there, you know, you are.
It doesn't mean we don't have to look at the cost, but there are
no,
other
you have
drivers
to look at the cost,
that we should look at first.
I agree. The CMOS technology really opened a lot of structure. So we have to keep an eye. Like, for example, we were doing quite interesting development with AMS. And AMS now is not interesting at all. They have a big contract with, I don't know, with some company. And so they practically said, we don't do it anymore. We have some foundries that have similar processes, go to these foundries. So again, you know, we are small, we are big, our area are big, but we are also small in comparison with the standard, you know, what is needed by Apple for the iPhone or whatever, you know. And so really, you know, we have to keep an eye because, you know, what happened at the beginning is that we started to see that when we submitted the design, it was coming back very late. And then they said, well, we are not interested, you know, there is another foundry, which is called TMC, that can do it for you. And for example, the Mu-Free collaboration is starting to look at this new foundry so they are starting to go to bring back a device that is called Mu-2E8, and they're checking this, that they've fabricated with AMS, and they're checking it with new foundry to see that in fact everything goes well. So we have always to be watchful also, you know, because you know, we are big, but we are small. If
I'm allowed one more comment before we hand over to that part of it. One thing I missed in this discussion is power management, right? We know we can meet that very tight material budget or nearly with some of these technologies, but we also know we can't keep them on all the time. At some point, then you have to bring in cooling pipes, liquids, etc. And then
you do a lot of nice work for that.
and I'm sure you in Oxford have.
And
right?
we are
so
doing
one
some
solution
nice
is
work
in
for
the
LHCb, yeah.
Right, microchannel cooling is maybe the answer there. I think but we're investigating for the ILC, but it makes much more sense here. And it's something that's coming. I'm not sure if it's ready in time. And there is always material associated to the cooling.
We have to keep an eye. And again, for example, for this mu3E, I think that, again, they are doing an interesting cooling concept. The ladder, we are building some of the ladder in Oxford for mu3. They're so light. I mean, it's unbelievable. They're just a couple of layers of very thin Kapton, and it's really cool. So we have to keep an eye also in this small project where you can put state-of-the-art technology, and you can really learn how to do things.
So just a comment about this large-scale silicon tracker. So as Daniela said, with the CMOS sensors, it's quite sure that there is a chance to make these much cheaper. But just one comment to what was said before. I think if the tracker cost is negligible compared to calorimeter, it's a bad sign because, I mean, then I think the money is not well balanced. I mean, the tracker is, of course, the essence for all the particle flow and things like this, and calorimetry, of course, should play a major role. But we had many examples in the discussion where I think we are not paying enough attention to very basic questions of global optimization. Okay? Many of us are completely into full simulation of whatever exists without thinking about the very basic things, whether things are in the proper proportion. And I think that would be a good thing, to not go for these fully optimized pseudo monsters, but think in very basic terms, because lots of technology that became available in the last 5 years, I think we have not fully integrated the possibilities of this into our thinking. So I think would be good to go back a bit to the conceptual level now, because the time scale is still long enough such that we can take into account all these developments in the full optimization of these detectors.
Werner is always right. I couldn't have said it better, yeah. And again, one of the things that we have to remember, though, also that when we go to smaller and smaller CMOS technologies, the non-recurrent costs become more and more expensive. So again, it's something that we have to think, because as we have done for RD53, for example, for the Atlas and CMS chip, we really have to think about pulling together the strengths in order to do this submission. So talk, coming together at this kind of meeting, bringing the community together is important.
Beautiful talk, Daniela.
Thank you.
I want to ask you if maybe it's not in that session remit, but did you mention particle ID?
I mentioned very briefly with some of the options, yeah.
Because to the FCCE or CEPC physics, there would be a lot of very precise things to do. Sometimes precision in the measurement of a quantity is not identical to precision on tracks or individual event reconstruction.
Individual, yeah.
There are some things like the acceptance that needs to be defined at the 10⁻⁵ level.
Yeah.
You're not going to do this with Monte Carlo. You have to really think, what is it that I need to do? And it's not just the technology of the detectors, maybe, it's also how they are built. Okay, this is one particular question. The other one is about particle ID. What is the limit of all these particle flow algorithm, etc.? And at some point, we're hitting the masses of the particles. And if we know them, if we don't know them, we're making a mistake once in a while and errors. So I think it's interesting to know whether we need that particle ID and what it means in terms of detector technology.
Yeah. I showed you a couple of plots, for example, of
Yeah.
what this drift chamber could do in
That's
a
right.
couple of ID. Again, I think that more care has to be taken. I do think that once you go precision, if we, we have to do better than what we have done in the past.
Oh, yeah.
And that is really a place where I think we can do better. And I think that you're totally right, because when you're going after this kind of systematic, you said it beautifully again. So, I don't have anything to add. And if somebody wants to comment about particle ID more, you can.
Okay. Last one.
Has there been a study of 2 Tesla versus 3 Tesla field for the whole of the detector? Because FCC EE is using a 2 Tesla magnet,
Yeah.
and CEPC mostly 3.
Yeah. Emilia, do you know? Because you have been looking at these things more than I do.
I've been looking at the click case versus FCC-EE. For click, we can go up to 4 Tesla. For FCC-EE, we have constraints from the position of the compensating solenoid, which is closer to the interaction point, so the maximum is 2. The thing is, with the 2 Tesla, then we have to increase the tracker volume. So in this way, we compensate for the lower magnetic field. I don't have the answer. Yes.
I stay out of it, okay? Any more questions?
Yeah.
Oh, because I was up until 4 a.m., so I'm really...
From the calorimeter point of view, the tracker needs to be as transparent as possible.
Yeah.
So at the end, you have also to compare all the services, etc. And well, this was not mentioned, I've seen. So at the end, the comparisons of all the performances should include all this.
Totally. Yeah, it's totally important, yeah. I remember, like in CMS, that, we have this beautiful electromagnetic calorimeter, and sometimes, having a silicon sensor, and not, now we can do much better in terms of silicon sensor, okay? But again, it's maybe not optimal.
Not only the amount of battery, but uniformity.
Yes, yeah, no, you're right. Okay.
Okay. So, thank you very much.
Thanks.